this is very purely the cooperation inside Taiwan, although my collaborator is Japanese. So this is Rotospa in NTU. And also one of them is Misao Sasaki. He's one of the pioneers of cosmology and general relativity in Japan. So he's a very great guy. And he was a former director in Yukawa Institute and now vice director of IPM, and now he's also visiting professor in NTU. So this is like a collaboration inside NTU. And the topic is like this. Okay, and with cosmology, I think you might have seen this introduction many times, because in cosmology, our global purpose is to understand underlying physics in the universe. So we actually the scale is totally different from the previous session. So because we want to understand like how it universe evolves and how it begins and other function, how it evolves as a function of time. So that eventually we need to understand what what's the beginning of the universe, and also fundamental question: what the universe made of, how does it evolve, and what's the future of the universe. So we want to understand what's the content of the universe. So we want to know dark matter, basically the dark components, or maybe gravity law can be different from the general relativity because modified gravity. Okay, and particularly I'm interested in the acceleration. Universe now accelerating. So this is my main interest. So to tackle this problem, always the fundamental equations, the Einstein equations, and if you don't know what the meaning, so just right hand side is describing gravity. Okay, right hand side is the matter of energy content of the universe. So this equation say that once you know what's the matter or energy component of the universe, then this determines gravity. Okay, so this is like a rough picture of the evolution of the universe. Roughly, the initial potential given by C and V, and then universe expand. So universe expand, and then the matter components evolve due to gravity. So there's all the trade-off. Okay, there's the gravity and the expansion. But as I said, universe is accelerating. But as you know, all the force we know is always attractive force. We don't have repulsive force. So we need to kind of like modify this equation. So changing right hand side is called dark energy, which has a negative pressure. Okay. All right, changing left hand side means that we change the gravity law from general relativity. So that's why we call it modified gravity. Okay, so I want you to remind that there are three key quantities. So one is the Hubble parameter, this is the expansion rate. A is the scale factor, the time evolution of the expansion. The second is the growth rate of the universe. This is the derivative of the density field of the function scale factor, basically the time. And third one is a parameter which describes how this perturbation is deviated from the Einstein gravity. I'll explain a little bit more detail later. So anyway, to understand this quantity of accelerating universe, there are so many ongoing galaxy surveys. Okay, so we try to map the universe using galaxy distribution. And also, I always emphasize that there are lots of some very interesting projects ongoing, and this is the instrument is pretty much contributed by our institute. So we have full access to this project. Okay, and then what's the physics using this galaxy survey? Basically, we have gravitational lensing and gravitational clustering, and because I don't have much time, so there's only one slide. So left hand side is we have two steps to the galaxy survey. One is imaging survey, take a photo of the sky, imaging survey, and it can be done hyperspectral count. And the second step is a spectroscopic survey, you take a redshift. Okay, what we can do from imaging survey to gravitational lensing. So gravitational lensing is that if you observe the distant source, then shape of the galaxy is distorted due to the intervening matter distribution. Because the light path is bended by the gravity, it's a direct prediction from general relativity. So what you observe is something like this kind of feature. Okay, ordinarily, the shape of the galaxy is spherical, but this is distorted due to gravity. And if you write down a metric, then you can write down in this way. So if this psi and phi are zero, this just standard Lower-Smoker metric. But this is a perturbation. We have this small quantity deviates from this homogeneous universe. Okay, so what gravitational lensing measure is basically the difference between these two potentials. Okay, so we parameterize this by alpha. Okay, so in general relativity and with ordinary matter, if there's no neutron mass, then this alpha simply becomes 0. Okay, so this alpha determines deviation from general relativity. On the other hand, this spectroscopic survey is a bit more complicated, but basically we do spectroscopy, so we know the distance to each galaxy, each point of the galaxy. Okay, so then what we do is measure separation between separation between the pair, each pair of the galaxies. Okay, and measure so-called correlation functions. Okay, as shown here. So, so y-axis basically determining the excess of the probability you can find a pair. If there are more matter, then you have higher value as a function of the scale. Okay, and on the 100 megaparsec H inverse, you can see this small bump. Okay, so this, if you know, this is called volume across oscillations. Okay, so this size corresponding to the size of the universe when universe was 380,000 years old. Okay, so these are the physical distance. Okay, but how you measure the distance? Again, you need to take into account the expansion rate. So how you observe this peak give you how fast the universe expands. So that's why this determines the Hubble parameter. Okay, the Hubble parameter is affected by both cosmological parameters, matter density or curvature or dark energy. Okay, so that's why it's another key quantity. And you can imagine if the gravity is stronger, then you can always have a higher probability to find galaxy pair. So basically amplitude is depends on the gravity law. Okay, so this F, as I said, is defined as a derivative of delta by the time. Okay, that's why I say these three are key quantities. Okay, but these three quantities are determined by different ways. So this alpha is determined by gravitational lensing, and H is the expansion rate. Expansion history of the class sign, and F is the growth rate of the history. So they are all related to the acceleration, but different observations determine different quantity. Okay, that's why we propose the new measure that is this diagram. You can forget about F, just sigma is just F, H, and alpha. Okay. And in observation, people already done the constraint on this kind of parameters, and this is one of my old work. So the y-axis again consider this F parameter. Okay, so this determines how fast the structure grows. The other function redshift. So once you have observation, then you can put one point by measuring the galaxy distribution. Okay, and I did like the constraint the highest redshift 1.4, and now we have again future survey can determine this F quantity much higher accuracy. So this red point and the green point is an expectation. This is not a real observation. Okay, and I put like two lines. One is the general relativity and one is the molecular gravity prediction. So by measuring this F, you can distinguish different molecular gravity theory. And this one is independent of alpha because I'm not using gravitational lensing here. And yeah, this is a bit more complicated. These are two parameter fits. It's x-axis is F and y-axis is Hubble parameter. And so if F is too high, this suggests a stronger gravity than general relativity, and smaller quantity predicts a weaker gravity. And this cut lines corresponding to the case of this equation of state with dark energy is -1. That means that it's same as cosmological constant. Okay, so we, by doing this kind of diagram, you can constrain how this acceleration determine. I mean, what's the source of the acceleration? These are all observations, okay, alternative data analysis. So look like our suggestion is not new, but it is a problem. They look like concerning the gravity theory, but this is sort of only consistency test of general relativity, in the sense that we assume that, because first, when you test the theory, you should assume the gravity first. Okay, and then see if the assumed gravity is consistent with data or not. So here, look like we are testing the deviation of general relativity, but we are not doing anything beyond general relativity, assuming general relativity. So it kind of like makes sense to consistent with general relativity. So that's why you call it consistency test. So what we want to propose is what we purely theoretical. We consider very general gravity theory, so-called Horn-Densky theory. It's a generalized scalar tensor theory. And we use this diagram and how given gravity theory is determined by this diagram. Okay, this is the motivations. And I shouldn't say too much about the detail, but so as you know, equation is derived by the action principle and given by Lagrangian. Okay. And if you remember general relativity, the Lagrangian for the general relativity is given by the scalar, rich scalar, curvature and cosmological constant. Okay, put this into the action, then you can get the Einstein equation. But this Horn-Densky, the generalization of Einstein gravity. So we have actually many Lagrangians. Okay, some of these one give you the Horn-Densky Lagrangians. So general relativity is included here. If you keep only L2 and just put 0 to all the 3 terms, then this reproduces the general relativity. Okay, but thanks to the detection of gravitational wave, we know like some speed of gravitational wave is already very similar to the, very close to the speed of light. So this observation already dramatically simplify the Lagrangian. Okay, so now allows Lagrangian only this, L5 only 0. Okay, so now all the important parameter I mentioned at the beginning is analytically determined. Okay, alpha is like this, and the delta is solving by solving the evolution equation for density perturbations. Okay, so just consider the multiple model I consider in this paper. So WCDM is just the simplest dark energy model. The equation of state for dark energy is just minus constant but not -1. It's just slight extension around CDM. Or if you replace the rich scalar by the function of R, then this is called FR gravity. And many others. Yeah, because so and this is a key plot. This is only the figure I will show you in this talk. So again, the point is in this plane, okay, different observation determine different quantity. Okay, y-axis is coming from the growth rate from the galaxy clustering, and x-axis is the expansion rate of the galaxy clustering, and this x-axis is from gravitational lengthening. Okay. So if you look at the easiest one, just a double CDM model, then you can see this kind of trajectory can be seen. Okay, and this is very easy to understand because okay, F smaller means the weaker gravity. Weaker gravity is equivalent to the first type function rate. Okay, so that's why we have this line. And this model has a alpha to be 0, so we don't have this plot on this side. And if you consider FR gravity, for simplicity here we can assume that the expansion rate is the same as lambda CDM. Okay, so x-axis for this is the same, but you can see non-zero alpha on this plane. Okay, so this means that if you combine the gravitational lensing and clustering, you can distinguish these two gravity models. And I put some number because this FR the parameter for this kind of FR gravity. If this quantity is 0, then this lambda CDM it comes to the alpha 0. And if you increase this value, then it goes to higher alpha. I think I'm running out of time. So this quintessence model, again, this is a so-called minimally coupling model. So this also doesn't give alpha. So it's alpha is 0. And it's gives very similar behavior with the double CDM. And this is a silly model because in observation we can see if you consider dark energy from observation, okay, high resolution you can do use the quasar or Lyman forest, and low resolution you can do with galaxy. Then actually you can fit the oscillating dark energy model for the data. Okay. And if you're familiar with observation, of course people doubt that it's just observation systematics, right? But still theorists think that this is physical. That's why people propose oscillating dark energy model. And anyway, we can rule out this kind of model using this kind of plane. Okay, so it counts this part, but it's ratio dependent. So here we assume ratio 0.5, but if you go to ratio 1, then this content goes to this side. Okay, it oscillates. So this is very easy to rule out from the observations. And if you want to make this alpha to be very large, you can see this is a very small value, but I could make it logarithmic scale. You can see this it's a very crazy model, but this gives you the alpha to be 1. So this kind of model can be constrained using the Gaussian ranging very well. Okay, so this is the use of this diagram. And this is a potential data consistency test. Okay, still error is large, but future study make this error much smaller, so that this diagram will be very useful. Okay, I hope I convinced you that the importance of this diagram, and this is a conclusion. I think I'm running time, so I stop here. Thanks.
So thank you for your talk. So we can have questions.
Well, by adopting modified gravity theory, if speed of light or Lorentz invariant in general will be modified a bit, then I think it can be independently checked by observation. How do you think about it?
Right, but so when this Gaussian wave was detected, speed of light of the Gaussian wave was very precisely determined, order of 10 to minus 5, and it's very, very precisely equivalent to the speed of light.
How about other Lorentz invariant? So I think your theory can be independently checked by some observational tests.
No, I think Lorentz invariance is not broken in this.
Not broken down.
No, I think.
Interesting. Thank you.
Today I was wondering, the people use modified gravity is try to explain about some of the smaller structure.
Yeah.
Because not like maybe like for example diameter simulation, the 4 diameter, 1 diameter. I was wondering is in the modified gravity theory used in the cosmological scale, how does gravity, how the physics vary from the general relativity in the
Great. So I think the more easy example is the Mondo. The Mondo is to explain the rotation curve with a dark matter, and that one is nothing to do with the first principle. Okay, but here what I say with model gravity is the Lagrangian is modified from the general relativity. So and then what kind of physics you consider? So Lagrangian already has a physical meaning. So if you want to make the oscillating solution, then you can keep some Lagrangian. So this is a way. So this is nothing to do with model. Yeah, I hate models.
Okay, are there any other questions? Okay, yeah.
But to me, I'm not familiar. There are infinite possibilities of modified gravity. But is there any principle you chose?
Yes, because first of all, deviation from general relativity should be small because general relativity is not proved to be very precisely correct. So, only the motivation is like this cosmological constant has a problem. If you produce the vacuum energy, and then this is like a 10 to 100 magnitude deviate from the observation. So, and also as I said, the speed of light of the wave is very well determined. So this actually excludes most of the motor gravity model already. So this kind of like only the surviving models.
Okay, so I think we are out of time. So let's thank the speaker again.
Thanks.